So now we're going to do a couple of word problems, it looks like, that involve logistic functions. So, are my notes correct? Are we ready for letter B? Or no, letter 6, or number 6.
Yes.
Okay, so we're ready for number 6.
Excuse me, Miss Ford.
Yes. Yes.
I have a college visit at 11:30, so I'm going to leave the Zoom at 11:30. Is that okay?
That is absolutely perfect. Good luck. Have fun.
All right, thank you.
Okay. So, letter 6, or number 6. The number of students infected with the flu, wow, how interesting, is given by this equation. What was the initial number of infected students? Does anybody remember how we find the initial value for anything, any kind of function, whether it's this or exponential? What do we know about the initial value?
T is 0.
Exactly. The initial value corresponds to the ordered pair that represents actually the y-intercept, where x, or in this case t, is 0. So we're just going to plug in 0. And as is always the case, when we raise something to the 0 power, I don't care what it is, this happens to be e, but it could be 32 or the square root of 19. It doesn't matter. If you're raising it to the 0 power, it basically disappears because it becomes 1. So we have 80 over 50, or 800, excuse me, over 50, which is, what, is that 16? So there were 16 kids originally infected with this disease. When will the number of infected students be 200? Now we're back to this equation. This is the equation we're using. So what do you think I ought to do if I want to know when I'll have 200 infected kids?
Plug the n with 200.
Right here, yep.
Make y 200.
200, yep. So 200 equals 800 over 1 plus 49 e to the negative 0.2t. Now, the other day we had something like this, and I remember telling you that when the exponent is a variable, we need to use logarithms. Do you remember that conversation? So we're going to need logarithms, not just yet though. What do you think we might do first? Don't jump in and do logarithms yet. What do we need to do?
Multiply 1 plus 49e to negative 0.2t to the other side.
Yeah, so we need to, I'll put this over 1 and cross multiply, or just multiply this over to here. So we have 200 plus, what is that, 9,800? E to the negative 0.2t equals 800. So we multiplied this times 200, so we have to distribute it. And then we have 800 over here on this side. Still, no logarithms, not yet. What do you think we need to do next?
Subtract 200.
Yep, so we have 9,800 e to the negative 0.2t equals 600. Subtract the 200 over. Still, no logarithms. There's one more step we have to complete. What do we need to do?
Divide 9,800.
Yep, we're going to divide. And rounding off can cause big headaches. So let's go ahead and leave that as a fraction. So it'll be 3/49. Now again, if you're not sure how to do that, you certainly could simplify it by hand. There's nothing wrong with doing that. You can also divide by 9,800. So 600 divided by 9,800. That gives you a decimal. And then just use your math button and hit math, and then frac will already be highlighted. Just hit enter a couple times, and it gives you 3/49. Now, at this point, we're going to take the logarithm of both sides. Now, when I do that, I have a choice. I can either LOG or I can LN. Both will give you the right answer. If your problem has an E in it though, it is going to save you a step if you use LN, because LN is a log base E. And one of the properties of logarithms that I hope we get to today, if not today, tomorrow, is that whenever you have an ln and an e back to back, they cancel each other out. They are inverse operations, so they cancel each other out. So we have negative 0.2t equal to ln 3/49. Then we're solving for t, so we'll just divide. So we'll take ln 3/49 and divide that by negative 0.2. The only caution I have for you here is make sure that when you do 3 divided by 49 that you close those parentheses before you hit divided by negative 0.2. And this is in days. So did you get about 14 days? It's like 13.966.
Yeah, I got
Okay,
that.
good. Good. Now, the next question says the school's going to close when we have 300 infected kids. So I want you to repeat this process, only instead of 200, now we're going to have 300, right? Everybody get that? So go ahead and see if you can walk through these steps, setting your equation equal to 300, because we want to know when are we going to have 300 infected kids. So I'll do it too, but don't look. You just see how far you can get. I got about 17 days. Did anybody else get that?
I got that.
Awesome. Anybody have a question about that work? We got one more example like this to do, it looks like, in the next problem. Anybody have a question about that? All right, let's look at the deer problem then. The initial population of deer. Grace, do you know what to do to find the initial population of deer with this logistic function?
You plug in 0 for T.
Yep. So I'm going to put a 0 in for T. Is that one negative 0.2 also? Yep. All right, so when I put a 0 in there, this kind of becomes 1. Well, it does become 1. So basically, I have 1,001 over 91. Which is 11. So we started out with 11 deer. Is that okay with everybody? All right, now we got another situation where we want to know when, that means I'm solving for T, when am I going to have 600? All right, so let's take a minute and go through that. You just did it. You just did that. So I hope the first thing you're doing is multiplying that denominator over. I got about 24 and a half years.
Yeah, I got that too.
Great. Is there anybody that's got a question about that? That process, everybody moving okay? You learned a lot about logarithms last year, so you're doing a good job. Okay. C. What is the maximum number of deer possible in the park? How are we going to figure that out?
You just take the numerator, it should just be 1,001 deer.
Absolutely. The maximum number of deer in the park, remember, this is a deer population, so it's growing. Remember, a logistic function has a bottom asymptote and a top asymptote. And that top asymptote is called the limit to growth, right? I mean, can you see? We're not going past that. And that we learned the other day is just our numerator. So the maximum sustainable population is 1,001. Can't have any more deer than that in the park, or bad things start happening. Like they starve to death. Okay, let's quickly get through a couple more problems here. Now we've got exponential growth. The population of Smallville was in 1890 was 6,250. It assumed it increased at a rate of 2.75% per year. Write the equation for me. Let's see. Ellie, can you give me an equation for an exponential? Now remember, exponentials look like this. Oh, not like that. Look like this. Can you give me the equation for this situation?
I don't know.
Uh-oh. Anybody know what A is? In a
2,250.
Yeah, in an exponential function, A is the initial value. So we are starting with 6250. It tells us that in the problem. And then we are increasing at a rate of 2.75%. Now, groupies, do not do something like this. If you multiply by 0.02, you are not increasing. What goes in this parentheses?
1.
1 point. That's exactly right. Remember, the number, your B value is either 1 plus the rate if it's a growth, or 1 minus the rate if it's a decay. So there's my exponential. Now I want to know, what will the population be in 1915? So using that equation, what will the population be in 1915? Anybody have a thought?
You plug in 50,000 for Y. Well, it says like predict the population when it reaches 50,000.
Okay,
Or am I on the
we're
wrong?
still doing A. We're still doing
Okay.
A. Estimate the population in 1915.
Then you put that in
for X.
What do I plug in for X?
Would you plug in 25?
Yes, I plug in 25. Now here's why, you guys. When did we start? We didn't start at time 0. This is the initial value when the time was 1890. So that's like our beginning. 1890 is the starting point. So if I'm going to 1915, that's 25 years. So I'm just going to put a 25 right here. I'm going to type it in on my calculator. That's easy. Round it off to the nearest whole person. So I got 1,2,3,1,5. So about 12,315 people. Now the second part of that question says 1940. What would I do for 1940?
plug in 50.
Yeah, I do
for X.
exactly the same thing, only that would be a 50, because 1940 is 50 years past my starting point, which was 1890. So 6250 times 1.0275. Oh, I didn't turn my calculator on. 6250 times 1.0275 to the 50th. So after 50 years, we have about 24,265 people. Is that okay with everybody? Make sure you're looking at all the details of the problem. Now, let's figure out when the population reached 50,000. Josh Ramsey, what do you think I'll do? Here's my equation. Well, that's an X. Here's my equation. What do you think I'll do if I want to know when the population is 50,000?
Once you plug it into X, wait, 50,000, hold on. I'm kind of lost right now. This is for
Okay. Who can help us out here?
You plug it in for Y.
Exactly. Remember, in this equation, Y represents the population and X represents the years. That's why in part A or B, whatever it was, that first part, we put in 50 because we waited 50 years. So 50 went in here. This is the population. So now I gotta put 50,000. And I have to figure out my x. So I know that means I'm probably going to need logarithms, but please don't do logarithms yet. What do I need to do to that equation first?
Divide by 6.
Exactly. Perfect. Beautiful. Divide by 6250. So 8 equals 1.0275 to the x. Now, this problem does not have an e. You are welcome to use ln. There's no advantage to it, but it's no extra work. ln or log totally makes no difference. I'm going to go ahead and log both sides. Now, nothing cancels. It's not like those last ones that we did. One of the properties of logarithms that I hope you remember, if not, we're going to review them in a few minutes, says that when you take the logarithm, so I just popped a log onto both sides. I took the logarithm on both sides. This side has an exponent. The exponent actually comes out front. So log 8 equals x log 1.0275. That is the beautiful thing about logarithms. Things that were exponents are no longer exponents. They're now coefficients. Meaning that I can simply divide both sides by log 1.0275, and I will have my x value. Again, caution when you type this in, log 8, close parentheses, divided by log 1.0275. So did you get 76.65? Now we need to be careful. That actually isn't the answer to the problem. Because the problem, what?
I'm sorry, I didn't get that.
Oh.
I got, like, were the logs supposed to cancel out, or do they not cancel out?
No. You gotta type log 8, close parentheses, divided by log 1.0275.
Okay, thank you.
So this is about 77 years after what? About 77 years after 1890?
1890.
Yeah. So we need to say, when are we going to reach that population? And it's going to be sometime in 1966, because we're going to wait a little more than 76 years. So it'll be sometime during 1966 when that population reached 50,000. Or you could say almost 1967. So either during 1996 or right before 1967. Does that make sense to everybody? All right, here we go. The 2000 population of Jacksonville, Florida was this, increasing at a rate of this. At that rate, when will the population be 1 million? Well, let's forget that last question and let's set up our equation. All right, Ellie, do you feel a little more comfortable now? Can you set up the equation for Jacksonville, Florida?
Is it y equals 736 6,000. I don't know what the B would be.
Yes, you do. It's increasing at a rate of 1.49%. So 1.0149. Remember, this is either 1 plus the rate of growth or 1 minus the rate of decay. So there's our equation. Now we want to know when the population will be 1 million. So Josh Ramsey, turn your camera on if you can, please, and tell me when you think or how am I going to figure out when the population's 1 million?
Do you put the 1 billion for the Y?
I do. Now I need to solve this very scary equation. I want to remind you that you got to divide first. I think we've talked about that a lot. And when I divide, those last 3 zeros are just obviously going to cancel. So I'm going to have 1,000 over 736, which I think I'll just leave alone. There's no benefit in doing anything with it, so I'm just going to leave that alone. Now I got an exponent up here. You cannot solve for that exponent unless you either graph it or do trial and error, or the best, quickest option, take the logarithm of both sides. Again, if you want to ln, that's fine. Everything I'm doing with log will be exactly the same with ln. You're just pressing a different button. The beauty of that, and the totally sole reason you did it, is because this guy is going to pop out in front. So you have the log of 1,000 over 736 equal to x log 1.0149. Don't panic about the ugly numbers. You're typing them in on your calculator. We want to know what x equals, so we're going to divide both sides by the log of 1.0149. And that's what I'm going to type into my calculator. Exactly the way I wrote it. Make sure you close those parentheses. So log 1,000 divided by 736, close parentheses, divided by log 1.0149. When will the population be 1 million? What are you going to say? How are you going to answer this? During what year?
2020.
Yep. During 2020. Because when you typed it in, you got 20.7. All right, we got one more, guys. One more, exactly like this, except it's not a population. It is an element that is decaying. Now, this is going to require us to think about a couple of things. It's an exponential, and I'm starting with 3.5. That part I got. I got that part. Do you have that part? You all right with that? That's our initial value. Now, what am I going to put in here? What is my B value? Take a wild guess.
Negative 2.5.
That's an interesting guess. I want to remind you though, Jacob and everybody else, that this number right here must be positive. Okay? So we're never going to put a negative number in here. We can have a negative number out front. We certainly can have a negative exponent, but we're never, ever, ever going to have a negative base. What does half-life mean? What am I multiplying by?
1/2.
1/2, yeah, 0.5 or 1/2. You can use the fraction, or you can use the decimal, whatever you're most familiar or comfortable with, doesn't matter. We're halving it. The half-life is the time it takes to cut what you have in half. Now, the exponent is not x. The exponent would be x if we were cutting it in half every day.
Is it x divided by 65?
It is. We talked about that the other day. We did some exercises where the first few were like, it increases by 25% every day. So our exponent was x. But then it said it doubles every 3 days. So then that means it's being thirded. Your days have to be cut in a third. Well, this is every 65 days, so we have to divide by 65. Before you even think about getting confused, stop. How many days does it take to cut it in half? 65. So if I put 65 in for x, x is the number of days. If I put 65 in for x, that would become a 1, and I would cut in half one time, which is what happens if you wait 65 days. So this is our equation. We want to know, okay, so that, well, this is supposed to be a t, sorry. So this is the answer to A. That's our equation. When will there be less than 1 gram remaining? What do I do? Less than 1 gram remaining.
This may be way out of left field, but do you have to like put in a less than or equal to sign?
I don't have to. I could. We run into problems with that with logarithms though, so I don't think I will, Jacob. What I'm going to do is I'm going to set this equal to 1, and then I know, let's say, I'm making this up totally, but let's say t works out to be 100. Then I'll answer the question by saying after 100 days. Because any time past when it equals 1, there's going to be less than 1. Does that make sense to you? So rather than kind of confuse the issue, I'm just going to set it equal to 1, and then when I answer my question, I'll take care of that other part. All right, so speaking of answering, how do I do it?
Divide 3.5 first.
Yep. So 1 over 3.5, and again, there really is no need to reduce that or simplify that. You can if you want, but please don't round it off. Whatever you do, don't round it off. If you want to write that as 2/7 or whatever, that's fine. Just don't round it off. Okay, now we'll take the logarithm of both sides. And the wondrous, this is the very coolest thing, that exponent comes out in front. Now we'll divide. And then this one's going to have an extra step, isn't it? After I divide, I'm going to have to multiply by 65. 117.478. Anybody else get that?
Okay.
Okay. So I'm going to answer the question and say, when will there be less than 1 gram? 117.478 is when there is 1 gram. So anytime after that, I will have less than 1 gram left. Very, very good. Any question about that at all? All right, we're going to spend just a couple of minutes looking at a couple of important properties. We are in no way going to get through this whole section, but once we get the hang of a couple of things, this section will fly. There really is hardly any work to show. You just have to have an understanding of a couple of things. So, one thing I'd like you to write down, maybe in the margin somewhere, is that the log base b of b to the nth is n. In other words, anytime you have a logarithmic expression and these two numbers match, the answer is the exponent. So when you look at problem A, you have the log base 5 of 5. What's the understood power right here?
1?
Is it
Yeah,
1?
5 to the first, sure it is. Yeah, don't doubt yourselves, you're right on target. 5 is the same as 5 to the first. We don't usually write that 1 there, but it's there. And the log base 5 of 5 to the first is just going to be 1, because when these two numbers match, the answer is the exponent. Write this down, gotta know it. When these two numbers match, the answer is the exponent. Now, that one was easy. This one you gotta think about for a second. In order to do this, we need these two numbers to match. So what do you think I'm going to do with the 16? If I need these two to match, what do you think I'll do with the 16?
Square root it?
Well, I'm going to change 16 into 4 squared. I need to rewrite 16 so it has a base of 4. So does that make sense to you? That 16 can be written as 4 squared? And if I do that, then the answer is obvious. These match, so the answer is 2. 2 more, here we go. What did I tell you about an ln and an e back to back? So the answer's 10. Now, that is actually an application of this property, because ln is simply the symbol for log base e. So what this problem really says is log base e of e to the 10th. Well, those match, so the answer is 10. Anytime you have ln and e next to each other, it's log base e of e to a power, so the answer is just going to be that power. One more. Anybody want to take a wild guess what the answer to D is? Can you figure it out?
Is it 1/3?
It is 1/3, Jacob. Very, very good. Guys, remember, this is log base e. You need this to be written as e to a power. Well, what do we know about radicals? Radicals are fractional exponents. And cube roots are 1/3 exponents. We did some practicing. For example, if I said to you, what's e to the 1/3, wouldn't you say it's the cube root of e? So this is exactly the same thing. We're just going this way. we're changing from a radical into an exponent. There are no radicals in logarithm land. You must convert your radicals into exponents when you're working with logarithms. So anyhow, the answer to that is, the answer to D is 1/3. Perfect. Okay, so tomorrow we have an optional quiz which we're all going to take. Remember, we did a practice quiz. It's over 3-1 and 3-2. And we're done for the day. Thanks, guys. Take care,
Thank you.
okay?
Thank you for the support.
All right.
Thank you.
We'll see ya.